Hello and welcome to this lecture. We're going to start looking at systems of linear equations. So one of the most useful, very widely applied technique for solving equations and solving problems is this approach of looking at it as a linear equation and figuring out how to solve linear equations. We already saw one example in the simple shopping problem of how linear equations can show up in applications. So we'll begin this study by first looking at three different applications where linear equations show up very naturally. Okay, all of these are very practical and very important today. We'll begin, given that we're studying electronic systems, we'll begin with the first one, which is circuits. Okay, so if you look at a typical circuit like this, which has two current sources of 1 milliampere feeding sort of a network of resistors, a simple network of resistors, one can solve for the currents and voltages across all the resistors by writing out what are called node equations. So you'll study this later on in the electronic systems classes, but I'm just showing you how solving for V1, V2, V3, which are the three voltages. Once you solve V1, V2, V3, find out the three voltages at those points, you have completely solved the circuit. You can find the current through any resistor you want. You can find the voltage drop across any resistor you want, and the entire circuit is powered through resistors. Everything you can find, right? So how do you find the V1, V2, and V3? It turns out there are three equations you can write, one for each node. Basically, the total current going out of a particular node is 0. That's what I've used here. You can also use total current coming into the particular node is 0. And you'll get three equations. And these equations end up being linear in V1, V2, V3. I've shown them here. I'm not going to go through as to how I got it. But the important point is these are linear equations in V1, V2, V3. So I got the first linear equation just by directly using the fact that current out of node 1 is 0, current out of the second node is 0, current out of the third node is 0. And then you see you can manipulate these equations, right? So V1 plus V1 is 2V1 minus V2, and then push the 1 to this side just to make it look a little bit better. But nevertheless, these are linear equations. And you see here, there are three linear equations here. Sometimes the right hand side is 0, sometimes the right hand side is non-zero. Some of the coefficients multiplying the variables, right? So see here, for instance, there is a negative 1, right? So 2V1 minus V2, which is minus 1 multiplying V2. And you also see here that, sometimes you have all three variables involved, minus V1 plus 3V2 minus V3 equals 0. All these three equations have to be simultaneously solved. So these are called systems of linear equations. All the three have to be enforced. How do you find V1, V2, V3 that solve all the three equations at the same time? Okay, so that's the technique we learn as part of solving linear equations, solving systems of linear equations. Is it obvious to you? Can you guess V1, V2, V3? Can you just try around a little bit? Maybe not that easy, right? So if you know the answer, you directly plug it in, but it's not that easy. So it's good to have a systematic method for this. How do you have an algorithm? How do you do step-by-step procedure for solving these systems of linear equations? Okay, so hopefully I've showed you one application where it's immediately clear that linear equations, systems of linear equations are going to come out. The next application is a very unlikely one. All of us have used web search, right? Google is very popular today. And at the core, inside, Google uses an algorithm called PageRank. Today, it's a very fancy version of PageRank, but initially, very early on, when Google started, PageRank was the algorithm that Google was using to put out the search results. So this is the idea here. Let me just show you how it works. With a very small illustrative example. Once again, this is just an example to motivate how PageRank works, not exactly the PageRank as it should be. Okay, so you search the web. Supposing you search for IIT Madras on Google, a whole bunch of pages will show up, right? A lot of pages are about IIT Madras. Which page do you show first, right? That is the problem which is non-trivial in web search, right? You have to figure out which is the most important of these web pages, which are all talking about IIT Madras. Okay, so how does PageRank work? How are these pages ranked, right? All these pages that are talking about IIT Madras, how do you rank them, and how do you show, which one do you show first? Okay, so clearly, I would like to show the most important of them first, right? And maybe if you have outside knowledge, you can guess something, but right now this is just a program, right? A computer program that has to look at all these web pages and somehow guess which one is the most important. Okay, so it was a bit non-trivial to come up with a solution for this problem, and it turns out you can come up with a very mathematical solution for this problem. And this is what has made Google possible, and millions and billions and trillions of dollars Google makes just by web search. And at the heart of it is this mathematical problem solving, which is behind it, and it's called the PageRank algorithm. Let me just give you a glimpse of how it works. So all these pages, let's say, for example, there was one particular search and 5 pages showed up. Okay, usually it's not 5, much larger than 5, but anyway, just for example. So I want to figure out which one is most important. How do I do it? I go look at links between these 5 pages. Okay, so these 5 pages may be pointing to each other, right? So which one is pointing to what? That is what I've captured here in this picture. Okay, for instance, the page 0 is pointing to page 1. That's why I put an arrow there, and then I'm showing, I've put an arrow here, and I'm showing that page 0 is pointing to page 1. Likewise, page 1 is pointing to page 2, but it's, guess what, it's also pointing to page 3. So likewise, page 2 is pointing to page 3 and page 4. Page 3 is pointing to page 1, it's pointing to page 0, it's pointing to page 4. Okay, like that. So what do I do first? I go first, there is a search string, somebody is searching for something. I have a list of web pages that are showing up, and I first form this web graph sort of thing, the graph that connects all these pages together. Each page is a node, 0, 1, 2, 3, 4, like that. And then I draw these edges or arrows which connect these nodes together, just to say what is important. So if you notice, for instance, if you search for IIT Madras, the logic, what is the logic here? If you search for IIT Madras, maybe you want to show IIT Madras's own homepage first, right? But what would happen usually is all these other pages which are talking about IIT Madras will always be pointing to IIT Madras, right? So the IIT Madras page will have a lot of other pages pointing to it, and that sort of enhances its importance. Okay, so instead of just using the number of edges that are coming in, PageRank uses a slightly more sophisticated method. What does it do? For every page that it wants to rank, it will associate a variable xi. So x0, x1, x2, x3, x4. And that is some measure of the importance of the ith page. Okay, some number. Okay, if that number is very high, then the ith page is very important. If that number is very low, maybe the ith page is not so important. Okay, I have a graph now. I have some linking between all these nodes, which are because of the how they point to each other. Okay, now I want to figure out which of these nodes is very important. And for that, I'm assigning one variable to each node, each web page, which is its importance. But now, notice, I have to have some relationship between these importances because of the connections between them. So that is something very, very important, and that is captured by linear equations. In a very, very clever way, that is captured. So let me just explain the first equation. x0 equals x3 by 3. How did that come about? Okay. Now, page 3, right, has an importance x3, and page 3 is pointing to page 0, page 1, as well as page 4. It's pointing to 3 other pages. Okay, so its importance divided by 3 should be contributed to the importance of node 0, page 0. The x3 divided by 3 should be contributed to page 1. x3 divided by 3 should also be contributed to page 4 because of these connections. Okay, because of these connections, of these connections, these three connections, you have x3 by 3 being contributed to the 0th page, first page, and the 4th page. Notice once again, why did I get the 3 in the denominator? That's because x3 is pointing to all 3 pages. So its importance divided by 3 should contribute to the importance of page 0, page 1, page 4. Now this kind of logic is, is very clever, and it gives you a very simple relationship. So if you go look at x0, x0 has only x3 coming into it. So the importance of x0, the only contribution it gets is from x3. So x3 by 3 should be the importance of x0. Okay, so that is the first equation. Think about it a little bit. It's not it's just logic to solve a problem. Okay, and when you write it down, you get this equation. So notice, look at x1. x1 has maybe I should do a different color here. Let's do red. x1 has something coming from x3, and it also has something coming from x0, right? Nothing else coming in. So it has an x0 coming entirely, right? x0 is coming entirely here, and x3 by 3 coming in from here, right? Because x3 is divided into 3, so x3 by 3 coming in here. So x1, the importance of page 1, is said to be equal to x0 plus x3 by 3. So you see here, these are all equations that we are coming up with to define our own notion of this importance of web pages, right? This is not a physical law. This is just a law that we are enforcing to make sure that we can solve for the importance in a consistent way. If I assign some importance to these web pages, they should be consistent with each other in some way. These are equations of consistency in some form. Okay, think about that. These are the equations that the creators of the PageRank came up with, right? The PageRank algorithm, you can go look it up, who created it. The founders of Google created it. They created these equations. They came up with these equations. Likewise, you have x2 equals x1 by 2. You see that x1 is pointing to two other pages. So x1 by 2 is being contributed to x2, and x2 has no other contribution from anywhere else. Likewise, you can write 5 equations involving these 5 variables. Okay, so there you go, a system of linear equations which is a solution to the web search, a proposed solution to the ranking of pages in the web search. So what do you do after this? You solve this system of linear equations and find out which xi is the highest, and you show that in the first as the first search result, or you sort it by decreasing level of importance, right? The highest goes first, next highest, like that, and you show that as the sequence in your web search. If you do this, guess what? Google, using this as the starting point, made billions of dollars. Okay, so linear equations are that powerful. So don't look down upon linear equations. They're really, really, really powerful, and being able to solve linear equations can make you a lot of money, right? Something important to remember. Okay, so having seen a very wonderful application like that, let's go to something a little bit more mathematical. So today, there are a lot of learning problems and other problems which are about fitting a curve to a set of data points. Okay, so here is an example. Different types of curves you may want to fit. One particular type of curve which we talked about very briefly are polynomials. So here is an example of, let's say, a degree 4 polynomial, which you write as ax power 4 plus bx cubed plus cx squared plus dx plus e, and its curve will be, if you plot this, you can plot this on Desmos and vary a, b, c, d, e. You'll see you'll get all sorts of interesting shapes. Okay, but what do I want the polynomial to satisfy? I want the polynomial to pass through 3 points. These are my 3 points here, 1, 0.5 that are marked in blue in this graph, 2, 2 and 3, 1.5. I want my polynomial to pass through these 3 points. What does it mean to pass through these points? The red curve that I've shown here is not passing through these 3 points. I want it to pass through these points, as in, if x equals 1, what should be ax power 4 plus bx cubed plus cx squared plus dx plus e? That summation on power and summation should evaluate to 0.5. If I put x equals 1, I should get y equals 0.5, right? So that's what should happen. If this were x, this has to be y, and that is, this y is this guy. Okay, so if you evaluate ax power 4 plus bx cube plus cx squared plus dx plus e, I should get 0.5. Likewise, if x equals 2, I should get y equals 2. Then this whole expression should evaluate to 2. If x is 3, this whole expression should evaluate to 1.5. Okay, that's what it means. This degree 4 polynomial has to pass through the 3 points. And surprisingly, maybe not very surprisingly, these three conditions, the fact that when x is 1, y has to be 0.5, when x is 2, y has to be 2, x is 3, y or this polynomial has to evaluate to 1.5, ends up being a linear conditions in the coefficients of the polynomial, right? I don't know a, b, c, d, e. I have to find a, b, c, d, e such that this condition is satisfied. It passes through these 3 points. And if I plug in x equals 1, what do I get? 1 power 4 into a, 1 power 3 into b, 1 squared into c, 1 into d plus e should be equal to 0.5. The coefficients has some power, but 1 power 4 is just 1, right? So this is just a plus b plus c plus d plus e equals 0.5. Guess what? That's a linear equation in the coefficients a, b, c, d. Okay. So you put x equals 2, you're going to get 2 power 4. 2 power 4 is just 16. 16a plus 8b plus 4c plus 2d plus e equals 2. One more linear equation in ABCD. You put x equals 3, you're going to get 3 power 4. What is 3 power 4? 81. 81a plus 27b plus 9c plus 3d plus e equals 1.5. So that's it. You have 3 equations in the 5 variables that are involved in your degree 4 polynomial. Okay. Again, you have a system of linear equations, and if you want to fit a polynomial through a set of points, you have to solve a system of linear equations. Okay. So to summarize, we saw 3 different examples. The first one was a simple circuit example. We saw that we got linear systems of linear equations. Second one was this wonderful PageRank algorithm for web search. Once again, we got linear equations involving the importance of web pages. And third time, we looked at a polynomial fit, a degree 4 polynomial. We attempted to fit it to pass through 3 points. And once again, we saw that we got a system of linear equations. So 3 different applications, 3 different ways in which the same type of equations come. And you want to solve these problems, you have to be able to solve systems of linear equations. Okay. So in the ensuing lectures, in the lectures that are coming up, we are going to see how to solve these systems of linear equations. And once again, our approach will have the same mathematical flavor. We'll start with simple cases and slowly complicate them, and end up with a general procedure for solving any system of linear equations and how to write down the answer. Okay, I hope you have a good time listening to these lectures. Linear equation solution is extremely important. We'll see it again and again and again throughout science and engineering, and all the best. Thank you.